Hello, it's James here. It's part 4 of openDog, the open source hardware and software dog robot. We're on part 4 and we've done quite a bit of development already, some prototype actuators with 3D printing. A lot of those pieces are going to be replaced with CNC aluminium. So today is actually the first episode we're going to try and make some of the actual final pieces, or at least the first pieces with the final design. So those are going to be cut out of aluminium. I've bought some plate already and we're going to have a go on the CNC machine actually cutting those out and trying to assemble some of it, starting with the body. Now I've not cut metal on the machine before, so we've got a bit of discovery to do on that, and there's also some 3D printed parts, so you can find out what that is in a minute, and hopefully we can get that main assembly together. But first of all, let's have a look at where we are with the design. So this is where we left off with the design last time. So we've basically got 12 motors in total on 12 degrees of freedom. So we've got legs that tilt this way, and the actuator here we prototyped last time. And of course we've got 2 joints on each leg. So that's 3 actuators per leg, which makes 12 because there's 4 legs. So I noticed in this there are a few issues. There's some symmetry issues actually in the messing around I've done with it. This isn't square in the hole, although the other one is, and everything else seems to line up. So what I've actually decided to do is go and sort of take that out and work on the detail for that part there, and also give this the correct colours so it matches the thing in real life. So there are going to be some 3D printed parts, which are all the yellow parts. These are mainly to hold the bearings to allow those square shafts to rotate in the hole. So there's an inner thing that's clamped to the 40/40 extrusion and a bearing bushing on there, and we'll look at that detail in real life because we're going to make those in this episode. And then we've got these aluminium plates and some more 40/40. So all of the plates, I can just take them away there, and those are the bits we're going to cut today. So we also have these pieces which are kind of spacers. We've got 6mm holes through this way which allow those to attach to the plates. And then we've got holes in the top here which are 4mm, and that allows the 3D printed parts to clamp to the extrusion. And that should hold everything rigid because we've got these parallel plates with more 40/40 bolted in the middle. So that should allow our leg mounts to be very rigid indeed. In fact, hopefully those 3D prints don't flex at all, because they're pretty much solid blocks. So the only thing I've made before on the CNC machine was my mini electric bike project, so have a look at that if you haven't seen it already. That's a bit of a practice of me getting to grip with the software tool chain and basically learning how to use the machine. So now we're going to cut metal. There's a few other considerations. So here's my piece of aluminium. It's 6mm plate, and I've got this 6mm carbide cutting bit which I got off eBay, which we're going to cut the parts out with, of course. Now of course this is metal, the plate is metal, and so heat building up is going to be a bit of an issue. So basically what we need to do is cut with the right speeds and feeds here, going quite fast basically with short depth cuts, and hopefully all the chips will fly off and that will take the heat away. But we need something else to help us with that. Basically we need some sort of cooling solution. So I've got some coolant, which is that white liquid. You mix it with water, and that's there for metal cutting, and it says what ratio to mix for various operations. And normally what you do with CNC is either pour that all over the part, you'd have a tray to catch it and recycle it, or basically you'd have something like this, and you'd use something called a fog buster, which basically fires droplets with an air compressor onto the cutting area and onto the workpiece, and that keeps it cool. And it's called a fog buster because basically it doesn't allow those droplets to disperse in the air to make fog, which is obviously bad to breathe in. So it keeps the droplet size really big, and that cools the part nicely because the coolant just sticks to the part where it's cutting. But I don't have one of those, so what we're going to do instead is just chuck compressed air down this tube to try and blow the chips away, and then we're basically going to mix this stuff up and brush it on with a brush as we cut and try and pull it round the cutting piece and hope for the best. Now the other thing we need to discuss is the tool path. So there's various trains of thought on how you should cut parts out. So it would be logical, of course, if we've got to cut a square out, to cut like this in 1mm depth cuts, go over it over and over and over, and that will cut a square out. But if you've watched NYC CNC, there's some other thoughts on that, which is that basically going in a straight line is actually quite bad for the cutting bit, because of course it puts pressure all round the end of the bit while it's cutting that slot. So as a lot of people prefer not to do that, they prefer to actually cut a much wider channel all round the piece and move backwards and forwards, or move in a circle and do that all the way round, and then do one final cut with the whole depth of the bit to cut the piece out. Now the other train of thought is that actually puts quite a lot of strain on the machine, and it concentrates the heat all in one place at a time, so it's hard to disperse the heat, and the aluminium might melt and stick on the bit. So the other train of thought is just to go in straight lines, because basically then the heat is left behind and the part has time to cool down again by the time the bit has to come back over the same part. And of course we've got that coolant and the lubrication. So I'm going to try first just doing regular slotting in a straight line, and we'll see how it goes. I've got 4 bits just in case I break one. So actually 6mm is probably a bit big. What we probably should be using is a 4mm, and I need to make some 4mm holes as well in the same pattern. So that's going to be a bit of a challenge we'll discuss in a minute. Ultimately I'm using 6mm because it won't snap so easily and I don't know what I'm doing. Eventually, once I've worked out how to do this, I'll probably go down to 4mm, and that'll cause less waste because obviously the channel it cuts will be smaller. I'm hopefully going to catch all those bits and all the offcuts and melt those down. So have a look at my forging and melting aluminium video that I did last week, and hopefully we can just get all those bits, gather them up, melt them down and make bar, and then machine it and use it for something useful. So we're going to be using a spire to plan the toolpath for this, courtesy of Vectric. Haven't quite got into Fusion 360 yet, it looks complicated. Obviously you can plan toolpaths in Fusion 360. I'm going to be using a spire because it's easy. So this is the first part we're going to cut out. We've so far planned 2 toolpaths here, one to cut it, the profile, and a drilling toolpath. So if we look in the 3D mode, we can go and preview that, and it will show us exactly what's going to happen. So you can see relative to the workpiece, the channel is actually quite big, which is why I think a 6mm bit is too big, and we should be using 4mm. Now, I also need to do some 4mm holes, which I can't do with a 6mm bit, obviously, because it's 6mm. So what I'm actually going to do is, where I want a 4mm hole, I'm just going to touch the surface with a 6mm bit by 1mm, and then manually centre tap the middle and drill it with a 4mm drill. Eventually, obviously, I should just be using a 4mm cutting bit and I can make 4mm holes, but for now, that's going to be the solution, so I can use a 6mm bit and it's less likely to break until I learn what I'm doing. Now, we do have tabs on the piece that will stop the pieces flying off, so those are about 1mm depth, and I'm cutting in 6 passes of 1mm each on a 6mm plate. So we have to be quite careful with the tolerances here. Obviously, the 6mm holes are no problem. This hole here, we need to make sure it fits on the 80/40 extrusion. So obviously with a CNC machine you have to cut round internal corners because it can't cut anything else because it's a round cutting bit, so that's a 3mm radius and we'll have to file that out. Hopefully this hole will be big enough. We don't want it too big, but we don't want it too small, otherwise I'll have to get the file out. So we'll do one, see how the hole comes out, and then take it from there. So I've just rigged up my air hose for my compressor here, and I've mounted the thing on the side here with a 3D printed plate that's just stuck on with sticky fixers for now. So it's just mounted up with zip ties and stuff for now. Obviously when I turn the tap, it squirts a jet of air on the cutting piece, so hopefully that'll be enough to blow the chips away. And as you'd expect, on the floor down here I've got a compressor that's got the pressure gauges and everything, and this one's quite good. It's got its own tap there, so I can turn it on and off remotely if I want to. So that's my coolant mixed up. It's pretty watery. I've done it between 5 and 10%, basically estimated, and we're just going to sort of drop that on the workpiece as we go. Right, some mistakes have been made, as you can see by my aluminium that's melted in these bits and this rackety mess. So basically my main mistake was my depth of cut of 1mm is far too deep. I've actually ended up regenerating the G-codes about 6 times and milling over this again and again and again. Unfortunately I didn't buy any more spare material. It started here, this is why this is the messiest. And basically I ended up with a 0.1mm depth of cut. Now I think I can go deeper, but I still need to sort out those speeds and feeds. So I was cutting there in the video about 40mm a second. I think it should be about double that, but I slowed it right down to try and work out what was going on. The holes, it actually failed completely drilling the holes and started to smoke. That was the last one it tried to drill, and that's because of course these are down cutters, so it's just forcing all the stuff into the hole and causing it to melt. I probably need a tool change to drill with an actual drill. In fact, what I'll do is just touch the surface with this bit, about 1/2 mil or something, and then I'll drill those manually on a drill press. I didn't even get to do all the holes because I had to stop the machine. So some lessons learnt there, but this is only the first one and we can move on and cut some more. Right, this one looks a lot better. I'm now cutting at 60 milliseconds. The previous one was actually only 20. I thought it was 40, but I was cutting far slower than that. I should be cutting at about 80, but this is obviously much cleaner. There's a little bit of melt around the top, but you know, there we go. We are just slotting in a straight line, so need to experiment with some things. I've brought those tabs down to 1/2 mil from a mil, so I can almost just snap that out. There we go, in fact, look. There we go, our first openDog aluminium part. So we'll clean that up and check the tolerance on the hole now. So a minimal amount of filing in the corners to get rid of those rounds, and that is a very good fit indeed. Now I didn't leave any tolerance for this. The, what is that, 80/40 extrusion is just below, like 0.2 of a mil below. And this, I did file a little bit on the sides just to clean up, but that is an extremely tight fit, which is excellent. So I need to just clean off where the rest of the tabs were and that sort of thing. And that's going to be excellent. So after a bit of cleanup, here are the actual parts. So that's the one that had all the melted stuff on, so I had to take an angle grinder with a sanding disc in to just try and clean all that up. But other than that, they're pretty good. The edges of these were pretty clean, actually. I've taken sort of a one of these sanding pads to it just to clean up the burrs and that, and a bit of a file just to get that tolerance on the hole there. But I'm pretty happy with those. So pretty happy with that. Other lessons learnt are that basically the compressed air on the little chute thing I put, the little hose, tends to blow the coolant away. So as you noticed in the later video there, I was just using the hand air compression tool thing there to just blow the bits away, and then going round again and putting some more coolant on. So we definitely need a fog buster, I think, or something similar, so they can blow the bits away and lubricate the part at the same time. At the moment, I can't really walk away from the machine. One of these takes about 30 or 40 minutes, because it's doing 65 passes of 0.1 millimeter. So it takes a while. It's not like a 3D printer where I can just leave it going at the moment, and I don't trust it anyway, in case it melts or burns or the bit snaps. So at the moment I'm standing there watching it, so it's a little bit time consuming, but we've got plenty of time to practice. The other thing is you'll have heard some screeching sounds now and again as the bit's cutting around, and that's when it goes and actually plunges to do the next level. Even though it's plunging 0.1 of a millimeter, it's actually not very happy about doing that with an end mill. So I think what I need to do is kind of ramp down over, say, 50 millimeters from where it is to the next 0.1 millimeter down, so it's gradually cutting with the edge rather than the end of the end mill. And there is a feature in Vectric to do that, which I haven't turned on at the moment. But we have 4 more pieces to do, so there's plenty of time to practice. And here they are. So I've cleaned those up, of course, and they're looking pretty good. Pretty happy with those. Got quite clean edges on and everything's good. I was cutting at about 70 milliseconds, still haven't quite got up to 80 yet. But we've got those little dips there where we need to go and center punch those and drill them in various sizes. So that's the next thing to do, and then we can begin assembly. So what's left in here? Well, there's a lot of aluminium dust everywhere. We really do need a proper coolant solution and something with that hose to kind of blow the stuff out of the way and cool the part at the same time with the lubricant. So probably need to get hold of a fog buster, then I can in fact shut the door and leave it going, instead of having to constantly go and get that brush and put the coolant on. Obviously that's not that great for my MDF spoil board either, which I probably need to do a flat finish on now with a big wood bit in here, so we can get a nice flat surface again, because it's probably going to warp. I'm aware there's other ways of holding metal, and that's still something I need to look at. So that's all the metal parts cut for this episode, but we've still got loads of 3D prints to do. So I've printed all these parts in 3D filler print premium yellow PLA, and that's that really good Lego yellow which I use for some of the giant Lego projects. The other reason for using that is it's a really good match for Ninja Flex yellow, which I'm going to be using for some of the flexible parts like the ends of the feet for now where it touches the ground. So these are of course our square spacers that go on that beam and have the plates bolted either side, and I've also printed the parts to hold a bearing. So that bearing holder is in two parts. There's one that fits on the end of the 4040, which is just there, and obviously the bearing fits inside the bigger one. They're a really tight fit. That fits in there, and that mounts on the end of the shaft there to give us that rotation, and that's the actual rotation of each hip. I've also made these caps to go on the end because I had the extrusion M5 tapped, so we can put that on, and that just overlaps the edge of the bearing to actually hold that bearing, so it's basically clamped in this gap right there, and that won't come off the end. I also put two set screws in there. They've actually got captive nuts that hold the screw, so it's got something to go into, and there's one on each side there. I could have of course put T-nuts in this 4040, but I think with that cap on the other side, that should be strong enough, being as there's a cap on each end of this extrusion as well to stop it slipping out. So I've assembled all my bearing pairs there with those parts and the bearings sandwiched in between, and these now of course fit to these plates, and I've got holes here. I actually drilled them out to 4mm, so I can just put a bolt through. I was going to tap the aluminium and then just sort of screw them on with machine screws, but I actually thought they've got to support the weight of the whole leg. The steel nut on the back will be stronger than the aluminium, so I might as well just drill through. There's plenty of clearance on the other side, and we'll just put some 4mm bolts and lock nuts on the back. Right, here they are. So I've made opposites obviously, so we've got two opposing pairs because that's how it's fitted. And now we need to use these and get all of this fitted on that big piece of beam. So there's one of those fitted. That's an incredibly good toleranced fit. So obviously I've bolted those up with bolts. My bolts are a bit long, but there's plenty of clearance again, and I've fitted that 4040 in there, which we need to talk about in a minute. So I've got two of those fitted with the right spacing. Obviously those are opposite pieces, and now we need to put the ends on. And then of course once we've got the ends, this bit of 4040 can sit in there, and here, and here, and that will rotate to make the actual hips. Right, so we're getting there. We've got one end done. I've taken the ends off here, these yellow parts, so that we can get the 4040s in easily by just shoving them in, seating them into there, which is a little bit tight. Ooh, there we go, and then putting those ends back on once that's pushed in properly. So there it is all together. So I just spin that round a couple of times so you can see it. Obviously we've got those rotating pieces for the legs there. I have installed the end caps on all of these as well. So let's just turn that around again, and so obviously it goes that way up. So yeah, pretty substantial. Obviously you can see by the physical size of it, it's going to be a pretty substantial robot. Already weighs quite a bit, but those actuators are pretty strong as we demonstrated last time. Alright, so now we need to talk about the holes that I've left in here. You can just see, which I ended up hand drilling. They're a bit rough, and obviously that actuator we put in last time. So what we've actually got is some extra 4040 that's not attached at the moment, and that's fitted on here. So that will actually be the thing that causes the leg to rotate on this axis, and that's pushed against here. So the actuator fits in there, pushing those, and that causes the hip to rotate. So there'll be a plate either side, and cunningly this should just bring us flush with this, which puts these two faces perfectly in line, which is pretty good. So obviously we've got that actuator we prototyped last time. I need to go back and change all of that plastic for metal. That's got some 10mm bolts on at the moment, and those will go through the holes here and another hole in this one. So there's two ways we could do that. I've actually left two little holes either side on these. The first way is to use some bushings. So I've just printed some little things to demo that. They would screw on. They'd obviously screw onto the T-slot as well. And they're just plastic things with holes in, and they would sit either side. And then basically they would of course go on there, and that would just allow that to rotate. Now it's not really high RPM. In fact, it never rotates once. It only ever does about 15 degrees in each direction. So I think that a plastic bushing would probably be fine, even against studding. There is another option, of course, which is to put bearings on there with a little cap like that that's got a bearing fitted in each side, and that would just slot on there. It's got holes in the back there, so we can attach that to the 4040 on the outside and bolt it on. We can make another one on here. Of course, I still need to drill that hole through the extrusion on both sides, and that will give us a perfectly good push and pull point. And obviously that whole actuator is supported on that axis there, and that axis there, so that has to be pretty rigid to hold it. So we've got quite a lot of length there between the bearings to put the nuts on either side. So that's almost the end of this video, but first of all I need to tell you about another openDog simulator someone has sent in. So check out the last video to see the one that was done in Unity. This one looks like it's been done in Python. There's a video, I'm not sure why it's flying. It's called Flying openDog. and there it goes, whizzing around. There's some physics there, and I'm pretty sure you can interface to those joint angles to actually simulate the dog. Of course, we're updating the CAD as we go, and anyone else is welcome to do anything with it as long as it's open source. So next time we're going to be working on this actuator again, hopefully making 4 of them with CNC metal parts. There may still be 3D printing on it, haven't quite decided yet, and fitting those in and getting those rotating pieces with the plates hopefully made either side, and then we'll be ready to attach the legs. So don't forget to subscribe for more updates on this project and some of the other projects, and also it's really important to say that all these projects are funded through Patreon. So have a look at patreon.com/XRobots and you can get access to some exclusive rewards, including a live stream with me and all my videos early. Alright, that's all for now.